Okay, here we go with example number 2 now. For these functions, a of x, b of x, we want, oh, and this is a typo. If everyone can change that right now, please. That should have been a 4/3 on the top. For a of x and b of x, we want to sketch the function y equals b at a of x. Well, if you remember composite functions, b at a of x means take a of x, which is x cubed, and replace it into this function wherever you see an x. So instead of writing b of x again, we're going to take everywhere we see an x here, 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 and here, and replace those with a of x, which is x cubed. So here is what I've done. I've replaced all of my x's in the function b with x cubed, x cubed, x cubed, and then simplified that. And if you want to pause to simplify yourself and see where this answer came from, that's fine. So this is the simplified version of b at a of x. X to the 6 minus 2x to the 5 minus 4x to the 4 plus 8x cubed. So this is the function then that we have to graph. Y is equal to this. Well, how do we graph this? So let's start with seeing what this looks like in factored form. The one thing I notice about these is that there is a common factor for sure, and that common factor here is x cubed. So I'm going to factor out x cubed first, and I'm left with a cubic function here. X cubed all the way down to 8. The next thing I notice, in order to factor this, you could, I suppose, look for testing numbers and then long divide out that factor or root. You can even use synthetic division to divide out that root. But what I noticed is that there's a commonality here, and that is I can common factor something out of this group, these first two terms, and that is x squared. I can also common factor out of something out of the next group of two terms, that's -4. And what's interesting is when I common factor each group, I'm left with x minus 2 here and x minus 2 there. That's what I noticed about this. If you didn't notice that little trick, it's not a big deal. You can actually find the factors very easily by, going through our testing method and then long dividing that out. But in this case, it ended up being very simple. And so we have x cubed times x minus 2, that's our common factor, times x squared minus 4. But as you all recognized, x squared minus 4 is actually a difference of squares. That's x minus 2 times x plus 2. Well, a better way to write this, as opposed to writing x minus 2 twice, is to write x minus 2 squared. That way we know we have order 2 on that root, or on that factor. There's also order 3 right here at x, which is a root as well, and there's order 1 technically on the x plus 2. So now that we're in factored form, we can actually figure out a lot about this graph. Let's take a look at what we know. Where are the x-intercepts? Let y equal 0, x equals 0 from this factor, 2 from this factor, or -2 from that factor. But at x equals 0, we're talking about an order of 3, and there's a specific thing that happens with order 3. At this factor, it's x equals 2, but order 2, and x equals -2 for the next one. Is there a y-intercept? Let's let x equals 0 and solve for y. Yep, y is equal to 0 is the y-intercept. What else do I know about this? Well, we have a leading coefficient that's positive because when I multiply 1 times 1 times 1, I get 1. That's positive. The degree is x cubed times x squared times x. That's 3 plus 2 plus 1 is 6. So if the degree is 6, which makes it even, there's a specific way that those graphs look. They either open up or they open down. And if this leading coefficient is positive, this is definitely opening up. So I wrote from Q2 to Q1, meaning from this quadrant, Q2, starting here, ending here at quadrant 1, as opposed to Q3 to Q4 down here. Okay, sign chart. I'm not going to go through this. You can pause it and try it yourself, but I will show you that I used -2 I use 0 and I use 2 as my tester, as my x-intercepts. Those came right from here, 0, 2, and negative 2. Then I chose testers to the left of negative 2, between 0 and negative 2, so negative 1 for example, between 0 and 2, like 1, and after 2, like 3 or 4. And when I plugged those testers into each of these factors, I decided what the sign would be for each one, and then I calculated the sign for y. Y meaning overall, for the function. Here, anything to the left of negative 2 was positive, which means it's above. Between negative 2 and 0 was below. And then both between 0 and 2 and 2 and above was above and above, plus and plus. So that tells me a lot about the shape of this graph, because I now know exactly where the graph is above and where it's below the x-axis. All right, let's start our graph down here by plotting the x-intercepts. One at negative 2, one here at 0, one here at 2. According to my sign chart, we start above. So because it's heading from quadrant 2 into quadrant 1, that makes sense to me that this section of the graph would be above. What happens at negative 2? Is it order 1? Yes, it is. X equals negative 2 is order 1. So it's going to pass, the graph will pass cleanly through that x-intercept down to about here. Remember, it's a sketch, so we don't know exactly where it's going to stop. Down to about here, let's say, and then back up. But what's going to happen when it approaches 0? When we have an order of 3, don't forget, we get what's called an inflection point. Not a critical point, but an inflection point. And an inflection point is like a blip. It does this. It doesn't pass cleanly through, it scurves through, sort of like this. It's curving through that point. So as it curves through, it creates that inflection, which tells me that there's an order of 3 or possibly 5 or 7. And as long as it's odd, it has to be an odd number as the exponent. And as it curves through x equals 0, it's going to be above, between 0 and 2, right? There it says above. So our graph is above, and then what happens when it approaches x equals 2? Well, that's order 2. And because it's order 2, it's going to create a critical point right there at that x equals 2, x-intercept. So the graph is going to curve back down, hit that point, and rebound back again because it's got a critical point. It's not passing cleanly through. It rebounds back again and then heads back up in the upwards direction towards positive infinity. And that's what creates that end behavior. It's the down through inflection point, curve, hit, and then rebound back up again. Both are heading straight up. Therefore, we do have a degree that's even, in this case was 6, and a leading coefficient that was positive.